In this video we're going over questions 6 and 7 of the OCR A Further Mathematics Stats paper of 2019. I've previously done questions 1 to 5 in earlier videos, and we'll go on to do the remaining questions after finishing this and then put together in a playlist. Question 6 is fairly recognisable chi-squared question involving Yates because it's 2 by 2. OCRA does state that they want you to use the Yates correction if you're dealing with a 2 by 2 contingency table. There are statisticians who disagree on this, but OCR explicitly say must use Yates, and even if it isn't said in the question, it's said in the specification. So we have to use Yates. We've got a contingency table. Let's set up the null and alternative hypothesis first. So the null hypothesis is there is an association. OCR8 seem to like you to use the word association. You will find the word independence used in it. They do accept it here, but OCR seem to prefer you to use the word association. So there is association between the city lived in and left-handedness. Bit of a mouthful, but I think that will do it. And it's okay to kind of abbreviate the next bit by referring to the null hypothesis before. So you could say there is such an association if you want to save a bit of time. So that's the hypothesis. Let's do the actual analysis then, do the actual test. The way this works is we basically work out expected values of EI, of what they would be if there was no association. So in order to do that, we need to add the rows and columns together. So if we add this row together, we get 23. And if we add this row together, we get 77. This column, we get 60. This column, we get 40. Okay, then to work out so for example, if we wanted to work out the expected of AL, that would be equal to the two numbers multiplied, the row and column number multiplied by each other, divided by the total number. It's fairly intuitive if you think about it. It's what the number would be if you expected there to be, an equal proportion of each of these as compared to the actual total, what's in the sample. That equals to 9.2. I won't show the calculation for all the other ones. Hopefully it's fairly self-explanatory. So our EI numbers for L and L dash and A and B, that one's 9.2. And if you do a similar calculation for this one, so this one would be 23 times 60 divided by 100, you get 13.8. And then this number here is 30.8. And then this number here is 46.2, doing a similar calculation for each of those. So then we work out our chi-squared, or what the deviations are, the sum of them, the squares, and remember that is equal to the modulus of OI minus EI, or the other way around, take away 0.5 over EI, and that bit squared. That's what the formula we're using is. So let's just do that for each of the columns, for each of the cells. That's 9.2. This is 14. I'm going to be consistent, so I'm going to take this number from this number and find the modulus of that. So it's 14 minus 9.2. Take away 0.5 squared all over the expected number, which is 9.2. And then for this cell here, we can do 9 minus 13.8, take away 0.5 squared, divided by the expected number, which is 13.8. And then we can look at this number here, 30.8. So that's 26 take away 30.8. The modulus of that, the absolute value of that, take away 0.5 squared divided by 30.8. And then finally for this one, we have 51 take away 46.2. The absolute value of that, take away 0.5 squared, all over the expected value, which is 46.2. When thinking of Yates, because you might have noticed I was I made sure I was consistent. I was taking this one from this one. It wouldn't matter if I did the other way around. Whether I'm using Yates or not, it doesn't matter because I'm squaring, and in the case of Yates, I'm modulating. But what I always think of is that when you're using Yates, you should always bear in mind that the Yates correction should be reducing each of these numbers here. So it's the absolute value take away 0.5. It's the absolute difference, which should be positive, take away 0.5 each time. So always think Yates has got to reduce the number it should be. So anyway, these numbers are 2.0098. I think it is good to write the numbers individually. 1.3398, just in case you make a mistake. It's easy to pick up the method marks that way. 0.60032 and 0.400216. So that gives us a number of 4.350. Okay, so then we need to look for the critical value in our tables. I'll just paste them in now. Suppose I need to talk about degrees of freedom here. The degrees of freedom is the number of rows take away 1 times by the number of columns take away 1. So in this case that's equal to 1 because you've got 2 degrees of freedom is equal to 1. It always is if you're using Yates. On that topic, just you only use Yates correction for contingency tables. We're not using it if you have another situation where you have a degree of freedom of 1. Apparently we only use it for contingency tables. So we've got degree of freedom of 1, so we're just looking at the first row there. These numbers here, by the way, we're never using in our hypothesis test. They're to do with whether the numbers are almost too closely matched to be suspicious in the opposite direction. But that's not really a hypothesis test, and that's not something you're likely to be asked. So we need to find the number that we want. The test was a 10% test. So 10% test is 0.2706. Obviously, because 90% is the difference between that and 1. So that's greater than 2.706. So try and use your common sense when it could, because I find that some of the students then struggle to come up with a conclusion. They do the numbers and then don't conclude. The numbers are deviating a lot from whether there was from if they were really independent or if there was no association. They are coming away from the null hypothesis. So we're rejecting H0 because the numbers are seeming to be too different, if you like, than if there was no such association. So now we need to have a contextual statement with some kind of vocabulary implying uncertainty. So there is significant evidence left-handedness of an association of left-handedness and city lived in. So we need, it doesn't have to say left-handedness, it's a bit of a mouthful, but we need to have the words in there that refers to the data. The factors, whether it's left-handed or not, and the city lived in. And we need uncertainty in our vocabulary. Okay, so that's the sort of hypothesis test done and concluded. Right, so now let's go back to the question for B and C. Right, now here they talk about conditional probability. State the relationship PL and PL conditional A according to the model implied by the null hypothesis. So this is why I prefer sometimes, even though OCR don't seem to want us to do it, to talk about the word independence and dependence when talking about chi-squared and contingency tables. But because basically, if we're accepting the null hypothesis, we're accepting no association. In other words, the L and A are independent of each other. So the answer there is that they would be the same. So question 9 is appearing there. Let's bring that down. Do that in a future video. So yeah, so we've got PL equals to PL conditional A under null hypothesis. Null hypothesis, that's it. Okay, and then part C. Use the data in the table to suggest a value of PL conditional A given by an improved model. Okay, well in this case, I would be looking at these numbers here. It's a bit of a mouthful here, but if L is conditional on A there, looking at it, we could actually account for those in the data here. And L conditional on A would be, if A's happened, we've got 23 occurrences there, of which 14 are left-handed. So PL conditional on A is 14, which is the total, divided by 23 under this new model. I'm sorry, it's quite sure what there's 2 marks for that, but there you go. That's the answer, 14 over 23. Okay, so now let's do the next question, question 7. Okay, I thought question 7 was a nice, relatively straightforward question to have relatively late in the paper. I hope you agree. It's all about kind of expectation algebra and the geometric distribution. First bit, we have this kind of principle that if you are finding the variance of a linear combination of a random variable, in this case a geometric distribution, any number added has no effect on the variance, which is fairly intuitive, I hope. And because the variance involves squares, we would have that being equal to a squared var x. So in this case, we'd have var of 3d plus 5 equals to 3 squared var d. And there are formulae for the variance of d. The variance of d is equal to 1, it's just equal to the 1 over the probability of it happening. That's the expectation, of course. What I mean is there is a formula for variance, but we're not even using that because we're given the variance here. So that's 9 times 40 over 9. So that equals to 40. Okay. Now part B, 6 marks for it, but it's not really. We need to work out the expectation of D in order to work out the expectation of 3D plus 5. So there's a few things to go through. Now there is a formula. It's given in the formula book. As I said, the expectation is 1 over P, but we're also given the variance of D will be equal to 1 minus P over P squared because it's geometric, and you're given this formula in the formula book. And we know that that's equal to 40 over 9. So we can set up a quadratic easy enough from that. We get 40p squared plus 9p minus 9 equals 0. It's okay to use a calculator there, but I'm old school. I end up with an irresistible urge to factorize. But yeah, it's okay to use a calculator. Obviously, the negative value of p is not relevant, so p is equal to 3/8. And as I mentioned, the expectation of d is equal to 1/p. So that equals to 1/3/8. So that equals to 8/3. And then we want finally to work out the expectation of 3d plus 5. Now using kind of that standard result, we're not squaring now because the expectation, 3 times the expectation of d plus 5. So that's 3 times 8/3 plus 5, which is equal to 13. And then finally, part C. Part C, we want the probability that d is greater than e to the d. Now this is kind of, again, I think it's pretty straightforward, but it's testing whether you understand the idea of the fact that geometric is discrete. So basically the main little kind of hurdle here is that we want the probability of d is greater than 8/3. Well, the only way that can happen, given the fact that it's discrete and it's getting discrete values that are integer values, is that the probability of d has got to be greater than or equal to 3, because that's the next highest number over 8/3. Now, it's geometric, so in order for d to be greater than or equal to 3, all we require, and this is intuitive, we don't need to use the formula for the geometric series or anything like that, all we really require is that the first 3 of them, it doesn't happen. So we've got the probability is 3/8, so we need the probability 5/8. It doesn't happen. I'll write it in. Let's write it in 1 minus 3/8, not 5, which is equal to 5/8, and that's got to happen 3 times for d to be greater than or equal to 3. It's got to not happen over the first 2 times. For it to be equal to 3 or greater than or equal to 3, it's got to have not happened in the first 2 times. So that's 5/8 squared. So that equals to 25/64. Okay, so that's it for this video, question 6 and 7. There will be a couple of other videos to follow, which will be the final 2 questions of this paper. Okay, I hope you found it useful. Bye.